Hi everyone, I'm Aisha from Center for Quantum Technologies. For today's presentation, I'm going to talk about generating quantum random numbers on a CubeSat satellite, SpooQy-1. Before I begin my presentation, I would like to thank my co-authors and our collaborator. The primary goal of our work was to demonstrate quantum entanglement in space. Because as a far-sighted target, we want to build a global QKT network. And for that, the demonstration of this quantum entanglement in space was the stepping stone, which we have achieved successfully. And later we thought that additionally, we can use our optical source to generate quantum random numbers. We can use the quantum shot noise of our optical source to generate it. We have two ground stations. One is at NUS in Singapore and one is at FHNW in Switzerland. And our satellite is in the low Earth orbit, and we have been receiving the quantum random numbers from our satellite at both of these stations quite regularly. So from this, we can say that this QRNG on board this nano satellite can contribute as a global randomness beacon for all off-grid platforms. This is a replica of our satellite. So there are many potential uses of QRNGs. It has uses in cryptography, telecommunication, financial system, simulation, gaming, and QRNG onboard an orbiting platform can be used to create randomness beacon. I have enlisted quantum random number generator here in these three classifications here: quantum short noise based QRNGs, entanglement based QRNGs, device independent QRNGs. For our work, we use the quantum short noise based QRNG. This is a very simple diagram of our optical source. So we have this SPDC based photon pair source. We are using the spontaneous parametric down conversion to generate the photon pairs. What it does, it takes a higher energy photon and it splits it into two lower energy photons, following the law of conservation of energy and momentum. And we have two liquid crystal polarization rotators that we use to select the basis of these photon pairs. And these two detectors, D1 and D2, we use them to detect these photon pairs individually. These detectors are actually silicon-based avalanche photodiodes. And this counting circuit, it records these coincident events per second, and we use the quantum short noise of these coincident events to generate the random numbers. Now, from the nature of our source and the SPDC process, we can say that these coincident events follow a Poissonian distribution. Let us take a look at a plot on the data that we generated in our lab. So these are the coincident events that we have recorded in our lab for 3000 seconds. And one thing that we observe that even though this entire experiment was running in the same setup for the whole time, there is some variation in the output. And this is due to the quantum short noise of the coincident event. And we are going to use this quantum short noise to generate quantum random numbers. So one may think that why we are using the coincident event count to generate the quantum random numbers. We can simply use a laser and detectors to generate the photon pairs. The reason is that the detector's detection efficiency can be impacted by non-quantum origin events. And these non-quantum origin events are uncorrelated events. And these uncorrelated events can be misidentified as coincident event by the detector, and we don't want it to happen. So how we can prevent that? So these coincident events linearly scale with the coincidence window. So the lower is the coincident window, the lower is the number of uncorrelated events. These uncorrelated events also called the accidentals. Let us take a formulation. So if we look at this formulation of accidental generation, we can see that S1, S2, and tau. So here tau is the coincidence window. The lower the value of tau, the lower is the value of this product of S1 and S2. For us, the value of tau is 2 nanoseconds, but principally we can lower it down as much as we want it to be. There is one downside of using coincident event count. The number of coincident events is significantly lower than the individual detection count. So when we are using this coincident event count to generate the random numbers, the number of random bits is also lowered. So far, we have seen the classification of Q-ranges, its uses, and our optical source. Now we will look into how we can extract the randomness from these coincident events. So we have already seen that the coincidence events follow a Poissonian distribution. So now if X is a random variable which denotes these coincident events, so then the probability of X equal to N can be written with this Poissonian distribution expression. Here lambda is the coincident rate. And we would like to take the mean entropy of this distribution, and it can be written like this. So after recording the coincident events in our counting circuit, we would like to encode these coincident events in k-bit register. And for our experiment, we have used a 16-bit register, and we are also computing the h-mean of the coincident event. So if we take a ratio of this, we can have the extraction ratio. Usually we get the value of extraction ratio from the experiment. For our experiment, the extraction ratio is greater than or equal to 1/4. There are many interesting approaches to extract random numbers from a system. We have used this L by M random Topliss matrix to extract L high entropy bits from M low entropy bits. And the ratio of L over M approaches the extraction ratio G. Here I have summed up some of the results and the parameter consideration for our experiment. And our size of encoding register is 16 bits. Extraction ratio is greater than or equal to 1/4. Randomness extraction rate is 80 bits per minute. And the probability of deviation from perfect random bits is 2 to the power minus 256. The interesting thing about quantum random numbers is its security, and the security comes from the unpredictability of the quantum random numbers. So the security parameter implies that if an adversary wants to predict the next bit in a string of binary numbers, he has to process 2 to the power 256 bits, which is practically infeasible. Here we can see some of the randomness test results that we have done on the data generated in our lab, and also the data that we have received from our satellite. So the optical source we have characterized in our lab, and the same replica of the source we have used in our satellite. So to justify the quality of the randomness, we have done a Borel normality test, and here we can see that the single digit of binary string have the same probability of occurrence, around some 50%. This 2-digit binary string has some probability of 25% of occurrence, and this 3-digit binary string has the probability of occurrence around some 14.7%. So the same digit of binary string has the probability of occurrence, it's equally likely. Now, if we also look at the data that we have received from our satellite, it also follows a similar distribution. Like the single digit has the 50% of distribution, the 2-digit binary string has some 25% of distribution, and so on. But there is some error bar because these data we are receiving from the satellite. So there is communication rounds and there is duty cycle, and for that we cannot have as many data as we can have in the lab. But if we can have as much data as we could have in our lab, we could have averaged all this, and then we could see that same of these plots would look similar. But in a nutshell, we can say that the data from our lab and the data from our satellite, it's random. So Apart from the Borel normality, we have also done two standardized randomness tests, ENT and dihydrosuit, on our data generated in our lab. For the ENT, we have got entropy 7.99 per byte, and for dihydrosuit, we have the within this range. So from this, we can say that our data in our lab also have passed this standardized randomness test. I have come to the end of this presentation. Let me just recall all the things that we have discussed so far. So we have implemented a quantum random number generator on board an orbiting satellite, and we continue to generate more random numbers from our satellite as it is still operational. And as a future goal, we would like to have a globally accessible public randomness beacon. There are already quite a few publicly accessible randomness beacons, so our contribution to that would be just a new feature in this quantum randomness beacon fraternity. And to that purpose, we will follow all the timestamping and authentication properly. This is a part of our group who has worked on the satellite project. That's all for this presentation. Thank you very much for listening. If you have any question, contact me here. And if you are curious about our research, you can follow us here. Thank you.